So I think a good starting point is to think about, what software would be like if software projects really worked properly. I think that we could expect as many software projects succeeding as failing. We could imagine as many projects being under budget early and delighting their users as over budget, behind schedule, and annoying their users. But I don't think that's what we think of as normal. I think that mostly what we think of is something like this. And I think that's saying something fairly profound about the way in which we think about and practice software development. I like this little GIF animation of the orbits of the planets in the solar system based on two different models of the solar system. This really is a way of representing the concept visually of paradigm shift. And this was a paradigm shift. So for tens of thousands of years, humanity held the view that the Earth was still and everything in the sky just orbited around the Earth or went around the Earth in some manner. And that all made sense. If you looked at the sun and the moon and the stars, they all proceeded around the Earth very nicely. And then there were these pesky things called planets. The word planet in ancient Greek means wanderer. And that's because these things didn't seem to obey any sensible rules. They just seemed to wander about in the sky. So people tried to predict where the planets would be, and they came up with models like the one that you see on the screen here, which is complicated, and you've got these funny curly bits in the red orbits of the planets. What that model is complicated and nasty to work in. What happened here in this example is that sometime later we had people like Copernicus and Galileo and Kepler come along and challenge that view and have a completely different perspective. They changed the perspective so that instead of seeing the Earth at the center of the universe, they saw the sun at the center of the universe. That's still wrong, but it's a much, much better approximation when you start talking about orbits in solar systems. So what's going on now is much easier to model, much easier to understand, much easier to predict. But one of the implications of this is that the rules for the new paradigm don't fit the old paradigm and vice versa. I think this is a very good analogy of what I'm talking about when we start thinking about and talking about software development. I think that we've got the model wrong for software development, and we need a paradigm shift. And really, that's what I want to talk to you a little bit about today. So what does software engineering really mean? Naresh and I were talking just before I started here about some of this, and I think to some degree the term software engineering has become devalued in our profession. We think about it as either meaning something nasty and bureaucratic and heavyweight, which doesn't allow us to do a very good job, or just means coding. And I think neither of those things are true. I think those are poor descriptions in either way. And I think one of the reasons for certainly the first of those interpretations is that we've got the model quite significantly wrong in terms of what it is that we're talking about. I think this is a fairly common view of what software development, software architecture, software design is for. It's about trying to fix the things that we can't afford to get wrong. What's engineering for? It's that. And I think that's partially true for physical devices like aeroplanes or cars or even donuts, but it's not really true even then. And it's certainly profoundly not our problem. This is not anything to do with the problem of software development for one really important reason. I think what that is based on, what that idea is based on, is really the idea of production lines and the ability to automate and regularize repetitive processes. That's not our gig. That's not our problem. One of the things that is really unique about software, and these days all digital assets, but profoundly true for software, is that our software, our stuff is, we come up with the design for some code. And that code is then generates a sequence of bytes that represents the systems that we're building. At that point, once we have that sequence of bytes, we can clone that sequence of bytes essentially for free. That's a freedom that wasn't possible, didn't exist before the concept of digital assets occurred, really. And now, what does production mean for our software? For a physical device, the production of many physical devices is a complex thing. For us, it's essentially free. We press the button, we can clone the bytes that represent our system for free. That's a very different thing. It means that the act of software creation is very, very significantly different from the act of other forms of creation. It means that our problem is almost entirely an exercise in design and not an exercise in production. The other thing to think about when we start thinking in terms of engineering is that all engineering is not the same. Engineering, if you're building bridges, is different than if you're building spaceships or electrical devices or chemical plants or whatever else. Each of these things has their own different uniquenesses. So one of the other things that we can be fairly certain of is if we come up with a discipline for software engineering, it will be ours. It will be unique to software and focused on the important parts of software. So one of the ways, but even when we take that into account, I think that we often have a fairly naive view of engineering anyway. One of the examples that I think is fantastic that we've got access to at the moment is the SpaceX effort to build spaceships that go to Mars. If you're at all interested in this kind of thing, you can watch world-class, cutting-edge engineering developing things that have never been created before live on YouTube. And that's a really interesting experience because it's not what we think it is. It's not some bureaucratic approach of just assembling all of these things. Every single one of these things, every change to one of these things is an experiment. This, starts with, you've got some kind of design and you're going to build some kind of craft like this. But to do that, you're going to try stuff out. You're going to evaluate, different parts of the system. This is a very early prototype of the Raptor engine that drives this spacecraft. And you're going to get stuff wrong. Things are going to blow up and stuff's going to go wrong, but you're going to learn from that. That's one of the properties of engineering. One of the hallmarks of engineering disciplines in other fields is that we try stuff out, we break things, and we learn from the breakages, and we find out how not to break in the same way again in future. And then we'll try small pieces of prototypes that we can try out ideas and experiment with, and stuff will still go wrong, stuff will still blow up occasionally, and then sometimes we start to get some successes. We can actually start to in this case, fly some of these devices. And we end up with functioning spacecraft. That's how real engineering works. That's how design engineering works, even when it's something as big and complicated as a space rocket. So I would argue that engineering, the kind of engineering that's closer to what we need to do, the kind of engineering that is interesting from our point of view, is always about exploration and discovery. So engineering is about exploration and discovery. Software development is about exploration and discovery too. One of the things that matters if we are in that kind of realm, and I think profoundly we are, is that what the implications of that is that if we are in the realm of always exploration and discovery to some degree, then we need to adopt the tools to become experts at learning. The first of those is iteration. We want to be able to make change in many small steps so that we have more opportunities to observe the progress that we make in each one of those steps. We want to be able to gather feedback. We want to collect information from our changes, our experiments, our evaluations, and understand what's going on. We want to make progress incrementally. We want to change our software development approach from trying to mimic some kind of illusory production line to being a more evolutionary approach. We want to incrementally grow the systems that we work on. I would argue I think it's a profound aspect of human creativity, not just about software development. If you look at the development of any complex system, it's a process of incremental evolutionary progress. Think for a minute about the first iPhone. The first iPhone was a remarkably crude device compared to a modern iPhone. And I'm certain that when they built it, the first version, they had ideas about changes that they would make in the next version and so on. But they had no idea where it would end up 10 or 15 years later. They didn't have that kind of picture. So the iPhone has been incrementally developed over time. You could say the same thing about cars or aeroplanes. The first cars were incredibly crude and dangerous devices, but over time, they've come to the point where we're on the verge of having fully automated self-driving electric vehicles that will, are remarkably safe in comparison to those early days. That's what real engineering looks like. We learn the lessons of the past, sometimes nasty lessons, sometimes lessons that involve hurting people, but we learn those lessons, we refine our engineering approaches to try and eliminate the failures of the past, and we just continue to grow incrementally. In software, we can make that incremental evolutionary approach to design much faster, much more incremental, much smaller steps. And we should. That gives us a better chance of gathering feedback and carrying out our experiments efficiently. Which brings us on to the next of these challenges. If we want to become experts at learning, we need to start working in more experimental ways. If we think of every change to our system as a form of experiment, that positions us well to be able to take advantage of the learning that we're carrying out. One of the fascinating ideas of these kind of combination of ideas, if you think about working iteratively, using feedback, making incremental developments and working experimentally, is it gives us an opportunity of hitting the target, whatever the target is and whenever it moves. Think for a moment of having some kind of goal in mind. And we're going to start experimenting randomly. We don't care what the experiment is. We're going to try something and figure out whether it moves us closer or further from our destination. So as well as the ability to make a change in small steps, we've got some kind of measurement that determines whether we're getting closer to our target or not. If we work this way in small steps, we carry out the experiment, we then measure to see whether it got us closer to our destination, whatever our destination was, or whether it took us further away. We eliminate the steps that take us further away, we keep the steps that get us closer, and over time we will incrementally, iteratively get closer and closer and closer towards the target. And that's true even if the target moves. So this is a profoundly powerful way of hitting any target that we choose to set. This is how all real learning takes place. This is how science works. This is how engineering works in other disciplines. This is how engineering ought to work in our discipline too. And the last of my 5 things for optimizing for learning, the thing that I think that distinguishes knowledge creation in engineering from knowledge creation in science, is the idea of being empirical. So we are profoundly practical as engineers, and it's really about what really works. So how we determine those targets, how we decide what success means for our experiments and our incremental discovery is important, and monitoring what really happens in production is a really valuable trait. Software development is also about managing complexity. We build systems that exceed the capacity for us to hold all of the detail in our heads. And so, therefore, we need to work in ways that allow us to cope with that complexity that we can't otherwise deal with. And in this category, there are another 5 things that can help us to do that. We want to work in smaller pieces. We want to divide the problem up into small pieces so that we can do work in one place without that work impacting on another. So we need to take the modularity of the systems that we create seriously. And to do that, we need to draw lines of abstraction in our design so that one module can interact with another module without knowing the detail of how that other module works. This is deeply important. And certainly there are some people, and I wouldn't argue with them very strongly, that would define, what it is that we do for a living in developing software as being nearly all about abstraction. We need to separate the concerns. We need to divide up the problems, the systems that we create, into pieces that are focused on part of the problem. Ideally, I would argue that we should be aiming to separate the concerns completely. So each part of the system is focused only on one part of the problem. And that makes for software that's easier to deal with. The complexity is managed. We're going to manage the coupling of these components carefully as well, with generally a trending preference towards looser coupling rather than tighter coupling, but actually it's more about appropriate coupling at the right levels as we're working through these things. And finally, we need to think about cohesion as well, making sure that the parts of the system that are closely related are close together so that we can deal with those in one place, and the parts that are unrelated are separate. That's the other end of the spectrum, the modularity part, so that we can change those independently of one another. All of these things are necessary for us to manage the complexity. I would argue that this gives us a practical definition for what makes code good, a practical set of tools with which we can evaluate the quality of our code and the systems that we build. If you think for a moment of two versions of a system, it doesn't matter what the technology is, it doesn't matter what the problem it's solving, but if you had two versions of the same system, one of them was modular, loosely coupled, good cohesion, good separation of concerns, and good lines of abstraction, and the other didn't, then which one would you prefer to work on? I think fairly obviously it's the first one. The first one would be easier to change, easier to test, easier to reason about, easier to modify, easier to understand where something went wrong and to fix, all of those things. The second one is almost by definition a big ball of mud that is going to be terrifying to work on. So I would argue that a good practical definition for good code is that it exhibits these properties. Once we decided that the code works, I would say that, the rest of these things are really what define the quality of our code. Yes, it needs to be fast sometimes. Yes, it needs to be secured sometimes. But those are kind of second order effects, and we can add those effects later if we've got these properties in our code. So, some principles for applying this kind of engineering thinking. We want to optimize for learning so that we can kind of explore and grow our understanding of the systems that we create and our solutions to the problems that we're aiming to solve with them. We want to optimize to manage or limit the complexity of the systems that we build so that we can work on them sustainably, continuously, on an ongoing basis, and be able to change them and morph them and shape them to meet the needs as the needs may change and as our understanding deepens. Some of the tools that help us to achieve these things are to start thinking of controlling the variables, to make sure that, when we're looking at our pieces in isolation, they are genuinely in isolation so that we can understand the impact of ideas and so on. We want to be able to make decisions based more on evidence rather than just guesswork. And so we want to run the experiments to try out our ideas and to evaluate them. One of the other lessons that we can certainly learn from science is to always start with the assumption that we've not got the correct answer yet. And that sounds like a kind of weird thing to say in many ways, but it's profoundly the better place to start. If we start out assuming that our ideas are perfect and we just push on ahead and they're not perfect, that's going to come as a surprise, and we probably haven't worked in a way that allows us to take a step back and correct them. If we start out assuming that our answers or design choices or understanding is incorrect, then we're going to be looking for ways in which it's incorrect, and we're going to take a slightly more defensive approach to design and implementation, so that when we find out how they're incorrect, we can fix that easily. This is deeply part of the philosophy of science these days. Scientists these days nearly always talk about ideas of falsifiability. So that's another idea that we can bring to software. Think for a moment of something like automated testing. What does it mean if all of your automated tests pass? It might mean that your software is doing okay. It might mean that all your tests are rubbish, or it might mean that your tests are really good, but you've missed the crucial thing that shows that something's wrong. What does it mean if one test fails? It means your software is not good enough. So we can never, ever prove that our software is good, but we can disprove it. We can prove that it's not good enough when we have a single failing test. So falsifying things is the stronger statement on the reality of our systems. And we can use that kind of thinking too. And all of these ideas, I think, are closer to engineering thinking than we would normally think of, if we were thinking in terms of software as a craft rather than an engineering discipline. One of the tools that I think profoundly amplifies our chances of doing these things successfully is to optimize for good testability. We're going to write code that's easily testable, or prefer code that's easily testable. And I'd like to explore that in a bit more detail to kind of see what that means. So let's think for a moment what it is. I've already stated my assumption that quality is based on modularity, cohesion, separation of concerns, and all of those good things. So what drives our ability to put that kind of quality into code in the absence of test-driven development? Well, it's kind of down to the skill, experience, and integrity of a programmer. There's nothing else that kind of forces us to do a good job of this. Test-driven development is something unusual. And it starts off by, it's best described by red-green refactor. And what we're going to do in test-driven development is that we're always going to write a test first, and we're going to run the test and see it fail. Now we're going to, once we've got a failing test and it's failing in the right way, we're going to write some code to make the test pass and see it pass. And then we're going to refactor the code and the test to make them clean, elegant, more general, whatever we want of them, while we're in the stable state of having a passing test. That's all great stuff, really good. But think for a moment about what that means in terms of our approach to design. The first thing that we're going to do is that we're going to write a test before we've got any code that makes that test pass. So what that means is that puts us in the position of a consumer of our own code. So we're going to design our code from the outside in rather than the inside out. Our job is to try and write this test to evaluate the behavior of this piece of code. Now, we'd have to be a strange kind of crazy person to want to make our own lives more difficult. So what we're going to do at this point is try and do this in a way that makes our own life easier. We're going to prefer code that's easy to test. So test-driven development automatically applies a pressure on us to generate more testable code. So what is it that makes code more testable? Well, obviously it has to work. Once we run the test, it should pass, and that tells us that it works. But it also needs to be more modular. We want to be able to test our code in pieces and evaluate those pieces of code in isolation of other pieces. We'd like them to be loosely coupled, so it's easy for us to tear out these pieces of code, and we're not going to have a horribly difficult time to get them into the state that we want them to be able to run our tests. We'd like them to be highly cohesive so that when we've tested them, we know that that behavior in the system actually works and that there's not some other sneaky part of the system somewhere else that's doing something similar and fooling us. And we want a good separation of concerns so that we can focus on just one part of the problem, focus our testing on evaluating just that, and not bringing in a whole bunch of other problems like persistence or UI considerations or whatever else it might be. And lastly, we want to have lines of abstraction. We want to have information hiding in the design of our system so that we can deal with one part of this system in isolation of other parts and maybe fake those other parts or whatever else it is that we want to do. So all of these properties that earlier I argued make a good definition for what we'd count as high quality in code are amplified by our ability to operate through test-driven development. What this means, I said earlier, I thought that test-driven development was unusual. So what this means is that in addition to the skill, experience, and integrity of an individual programmer, we use the skills of test-driven development to amplify those things that we value, and we end up with a sum that is greater than the parts. We end up with amplifying our ability to produce these nice, high-quality designed, modular, loosely coupled, highly cohesive systems with good separation of concerns and good abstraction. This is a kind of talent amplifier. It's not going to make a bad programmer great, but it will make a bad programmer better, and it will make a great programmer greater. And I think that's very unusual. I can't think of anything else that does this in quite the same way in software development. So I think this is a remarkably powerful tool to amplify our talent, whatever that might be, as software developers. I want to give you just a bit more concrete example to just show what I'm talking about. This is very simple example in code. So we've got here a car, and this car has got a petrol engine, and as part of this code, we've got a function that calls start, and that puts the car into the gears into neutral, applies the brakes, and then starts the engine on the car. Okay, so let's write a test for this piece of code. Here's my test. Should start car engine. We're going to create a new car. We're going to say start the car, and now there's nothing to assert. I can't actually do anything here. I could choose to break encapsulation and dig into the workings of this class. That's a terrible idea. I'm just going to end up with my test overly coupled to the solution. So we're in a bit of a mess now. So what can we do instead? So let's start looking from the other way around. So let's do the test-driven development thing. So should start a better car engine. So we're going to start off. What we really want to achieve is we'd like to be able to see that the engine started successfully. So why don't we write some code that says that? Let's just assert that the engine started successfully. And that's going to happen when we start the car, as before. So what that means is that we need to pass the engine to the better car so that we can hold on to a copy of the engine. And we're going to create a fake engine that allows us to do this. In reality, we might use a mocking library or something like that for this, but here's my implementation of a fake engine, just so you can see how that works. All this does is it just records the fact that start was called and then allows us to query whether start was called. So here's my better car now, and that's my implementation. It's very similar to the previous one, but it's different in this one key aspect. We're now passing in the engine. We're doing dependency injection in order to make our code more testable. But let's just think about the implications of that. So the first thing is that when we start thinking about this in production, we can still create a car with a petrol engine, which behaves in precisely the same way as the car did originally. It's going to do all the same things, except now it's testable. But the implications of that is that we've improved the modularity of the code. We've now teased apart better car and the engine, in this case, the petrol engine. And so each of these bits of code is a bit more focused on what it is that it's doing and more isolated than before. In one very practical sense, the better car doesn't know how to create an engine, whereas previously the car had to know how to create an engine. So that's reduced the coupling between those two, and it's improved the modularity. It's also improved the cohesion. So now all the stuff that's about petrol engine-ness is inside the petrol engine, and all the stuff that's about car-ness is in the better car, and they are separate. The car depends less on engines than it used to. In fact, it only deals with an abstraction of an engine, the engine interface in this example. And lastly, that line of abstraction is clearly defined. We now know what that is. So by making this trivially simple change to make my car more testable, it is more modular, it's more cohesive, it's got better separation of concerns, it's got looser coupling because the car no longer knows how to create an engine, and better lines of abstraction because those abstractions are more clearly defined in the interactions between the car and the engine. These are good things. The result of that is that we can create a car in production with the petrol engine. We can create a car with an electric engine. So the code's more flexible. We can use it in many more circumstances. And if we're some kind of crazy person, we can even create a car with a jet engine. This is just better code. And I don't think anybody would argue with that. And it's better. I didn't do anything else. I didn't think hard about the design. All I did was worked to make it a bit more testable. And as a side effect of just that, we've improved the quality of this piece of code. As I say, I think that's fairly remarkable. And I don't think that happens very often in software development. I talked earlier about the need to work experimentally, and that's deeply important. We've already talked about some of the things that add up to allowing us to do that. But we need to be able to take pieces of our system and experiment on those individually. And some of the experiments will certainly go wrong. And some of them we'll need to be able to take smaller pieces and evaluate those as kind of just experiments that we're going to throw away and not use in real production. And again, some of these things will go wrong. But that's the nature of experiments. If your experiments don't sometimes go wrong, you're not really experimenting. One of the superpowers of science and engineering is, in reality, we learn more when our experiments go wrong. And so at some level, we want our experiments to go wrong. Some of the explosions that I showed in the pictures from SpaceX were actually test pieces that they meant to blow up on purpose to see what would happen. We want to make progress in small steps, so we want to optimize to allow ourselves to work iteratively at a very fine-grained degree so that we can capture more feedback. We can use these small steps also to do the next important thing, which is to control the variable, gather feedback and control the variables. If we're working in small steps, predicting the results and controlling the variables, what this means is that we can really understand what's going on. The small steps limit the scope of our changes. If you make a change to your production system and you find that it increases user sign-up by 30%, is that a success or a failure? The real answer is that you don't know. If you released your change alongside 500 other changes, some of which also might have improved the value of the sign-up, you have no idea. If you focus down and you released only that change and your sign-up went up by 30%, then maybe you've got a result. Maybe not. Maybe the variance is different. So you need to look at this more scientifically and think about what the variables are, think about what the impact on your decision making is. But all of this allows us to focus in and have a better chance at solving the problems before us. I've been using this feedback picture to represent the ideas of continuous delivery for a very long time now. At the outside is the kind of core idea of continuous delivery. We want to be able to have an idea, get that idea into the hands of users, and collect information to discover whether it's a good idea or a bad idea. At the inside, we've got the very fast cycle that I've just been describing of test-driven development. And in between, we've got the use of executable specifications, acceptance testing to evaluate whether our system is deployable, configured correctly, does the things that users want, is releasable, and so on. This is deeply built into the practice of continuous delivery. And this idea gives us this ideal platform for carrying out a certain classes of experiment. This is one of my favorite quotes from most people's favorite physicist, if you're nerdy enough to have a favorite physicist. It doesn't matter how intelligent you are, if you guess and that guess can't be backed by experimental evidence, then it's still just a guess. So if we're looking to become more like engineers, we need to start moving outside the realm of guesswork and into the realm of experimentation, gathering feedback, managing the variables, and so on. Another of these tools that's remarkably useful and powerful is the idea of speed. If we optimize to shorten the cycle of our feedback and improve the quality of our feedback, what that does over time, it starts to drive out the costs that are inherent to our development approach. And that allows us then to start fixing some of those problems that we highlight by trying to up the speed of feedback and iteration. It drives out the problem and makes it more clear. That starts to get us focusing on trying to make the things that the way in which we're working, the engineering processes that support us, more repeatable, more reliable, more focused, higher performance, more efficient over time. That gets us into all sorts of interesting territory of, again, controlling the variables through version control, automating nearly everything, and so on. This is a picture of a deployment pipeline that I use to describe the mechanism that's at the heart of the ideas of continuous delivery. And the idea of a deployment pipeline is that we build essentially a machine that goes from commit to releasable outcome. We automate all of the creation, the production and validation steps on our routes to production. And this becomes our only route to production. So if we commit a change here, we're going to get fast feedback on whether our change is releasable. When I advise my clients, I usually describe them to look at this first part, which is largely focused on the design part of the challenge, the development team facing part of the challenge, and get feedback from here in under 5 minutes. And then the second part of the pipeline is all focused on the releasability of our changes. Does it do what our users want? Is it configured correctly? Is it secure enough? Is it fast enough? Is it regulatory compliant? And so on. And we automate all of that too and get an answer back. I usually shoot for under an hour. And that leaves us then with just being able to push the change out into production. I was at a conference not very long ago that Alan Kay was also attending, and he described engineering as design, simulate, and build. And this model that I've just presented absolutely fits that picture. So if we start off with the deployment pipeline, we feed our changes into here. This first part of the pipeline is all about the design problem. It's about giving fast, clear feedback on the nature of our changes. We get fast feedback on the quality of our designs through test-driven development, as I've already described. Then the second part of the pipeline is about simulating the behavior of our system in production-like environments in all sorts of ways that are interesting enough to us to allow us to determine whether that change is releasable enough. And that leaves us with what Kay calls build, but we just call pushing this out into production. That may be still a complicated part of the problem, but from our point of view in terms of continuous delivery, it's always simpler because we're just pushing something out that we know to be good because we've already simulated it in production and designed it well using these mechanisms. If it doesn't allow us, if whatever it is that we choose to do in terms of trying to establish an engineering discipline, if it doesn't allow us to build better software faster, it doesn't count as engineering. And that's really my primary argument. Engineering is the stuff that works. And so I think that's a reasonable statement to be able to focus on.